Hello again. Today we have the second lesson in chapter 11. We have SHM, which stands for Simple Harmonic Motion. Previously, we explained when we have spring and mass system. Today, we will explain the pendulum. So, the motion of vibrating a mass spring system is an example of simple harmonic motion as we discussed before. Simple harmonic motion describes when we have a force restoring force, and all the time restoring force must be at the opposite side. Because of that, we saw previously from Hooke's law, we must have a negative sign because all the time it must be at the opposite side or opposite direction. So here in this figure here, we have a simple pendulum which consists of mass called a pop. So here we have a mass. All the time the weight direction on the negative y-axis because of the gravity. So if we have here a theta, so we can resolve the weight into y-axis and x-axis. Since the theta here, that's mean the force on the y-axis is equal to F times cosine because it's close to the angle. And because of that, on the x-axis, it must be equal to F times sine theta. So first of all, we have to know that the force on the x-axis here is equal to sine theta. It's the Fg. Fg, that's mean the force, the weight force, which is equal to m times g. So here F on the x-axis equal to m times g, which is the weight force, times sine theta. Now,
vibrates or oscillates at a single frequency around an equilibrium point, it is moving in simple harmonic motion. Pendulums with small amplitudes and springs that are not stretched too far often move in simple harmonic motion. The velocity of an object in harmonic motion is zero at the outer points of its oscillation, where the force on the object reaches its maximum. The object has a maximum velocity at the equilibrium point, where the force is zero.
so again, all the time if I start from here, so assume this one is the position number 1, here the equilibrium point, which is the position number 0, here the position number -1. So again we have position 0 here, we have position number 1 here, and we have position number -1 here.
The starting force equals negative k times x, where k is the spring constant and x is the displacement of the object. Since the force is doing work on the line, the Baraa kinetic energy changes with time. Similarly, the elastic potential energy changes with time. However, the total energy of the system is constant. We have now converted light into strain. The kinetic energy is zero, but the elastic potential energy is at a maximum. The same is true of the body strain. At the midpoint, the potential energy is zero because the strain is relaxed. However, the kinetic energy is at a maximum. Because of this, the total energy does not change.
So again, now we will start from position number 1. So again guys, here's position number 1, here's position number 0, here's position -1. So if I started from here, from position number 1, so now the velocity is equal to 0. That's mean the kinetic energy is equal to 0. So on the graph here, the kinetic energy is on the green line, green curve, and the potential energy, elastic potential energy, it's the blue curve. So again, in position number one here, the velocity is equal to zero. That means the kinetic energy is equal to zero. And the green curve here is equal to zero. But since we have the maximum displacement, that's mean at this point here, point 1, we have the maximum elastic potential energy. So here the blue curve is at the maximum value. Now the next step here is position number 0, is the equilibrium position. At the equilibrium position, the spring is relaxed. That's mean the potential energy now is equal to 0. So the green curve now at the equilibrium position here it's equal to 0. And at the equilibrium position, the velocity is equal to maximum. That's mean the kinetic energy is equal to maximum. So here position 1, then position 0, then position -1. At -1, again the velocity is equal to 0. So the green curve is again here equal to 0. And we have the maximum displacement. That's mean again the gravitation, the elastic potential energy with the blue curve is equal to the maximum value. Don't forget, at any point the total mechanical energy must remain constant because it's all the time equal to the potential energy plus kinetic energy. So now, here we have pendulum and here we have spring mass system. So I will start with a position number 1 again. So here we have position number 1 in the spring mass system, and here we have position number 1 at the pendulum. So first quarter, it's from position 1 to position 0. So again, from position 1 to position 0, first quarter. Second quarter, from position 0 to position -1. Then third quarter, from the -1 to 0 again. Fourth quarter, from 0 to the position 1 again. That's mean the wavelength lambda is equal to 4 quarters. Again, from position 1, first quarter position 0, second quarter position -1, again to 0, and then to 1 again. So here we have 1 lambda, which is equal to wavelength. Now we have an example. If we have a mass of 3 kilogram, so here we have m equal to 3, is attached to spring scale with a spring constant equal to 36 Newton per meter. So here we have K constant equal to 36. What's the spring's displacement? For the given, we have m equal to 3, G gravity constant 9.81, and K 36 Newton per meter. To find the displacement, we knew before F, which is equal to mg, it must be equal to -kx. It's Hooke's law. So again, F, which is equal to the weight, m times g, equal -k times x. To find x equal to m times g divided by -k. So it's equal to m, which is 3 from the given here, times g, 9.81, divided by 36, is equal to -0.82. That's mean -82 centimeter. Negative, that's mean to the negative x-axis or to the negative y-axis. That's mean at the opposite direction. It depends if it's a vertical or horizontal. At the end, guys, you have a homework here. Please try to solve it, and here you can find the final answer so you can double check for the answer.